Hi there, we are the Recursive HaaS and Fast Provisioning team for CS 591 EC 500 Cloud Computing at Boston University. Team members are Lara Kampfonic, Quentin Lee, Michael Reevy, and Sahil Takali. Today we're going to take you on a tour of our semester-long project.
We'll go over a little bit about what HaaS is and how we're implementing Recursive HaaS and Fast Provisioning on top of that. We'll also talk about our project goals. This project is part of the Massachusetts Open Cloud Initiative, and it was a great way for us to get experience working on an open source project in an Agile Scrum environment. We'll show parts of the code in action and talk about what we achieved and what we learned along the way.
So first off, a description of HaaS, hardware as a service. Unlike provisioning a virtual machine on a traditional cloud service, HaaS allows users access to the bare metal hardware. For example, certain user applications can benefit from direct access to the GPU, without the layer of abstraction introduced by the VM. The figure on the right shows a HaaS installation with 2 user projects. These projects are separated on the network layer at the switch. Users can add nodes to their projects from the free pool if they need more resources, or release them if they are no longer needed.
Our project deals with Recursive HaaS. We can think of a Recursive HaaS user as a customer of base HaaS. In the figure on the right, we can refer to user 1 as a Recursive HaaS instance. User 1's nodes can be provisioned by other users to create separate, isolated HaaS projects. In this scenario, base HaaS handles the network configuration of the Recursive HaaS user. In our diagram, user A and user B only interact with user 1's Recursive HaaS server. If commands require interaction with bare hardware, they are passed through to base HaaS. This topology can be extended many times over, where we can set up HaaS on top of HaaS on top of HaaS. You get the idea. The upshot to all this is new HaaS functionality can be tested on Recursive HaaS instances before fully implementing them on base HaaS. Also, trusted networks can enable features like fast provisioning, but more on that on the next slide.
Fast provisioning is a new feature we wish to include in HaaS. It serves as an excellent test case of implementing new functionality using Recursive HaaS. As the name suggests, fast provisioning is a solution to reduce the time to service of physical nodes. Traditionally, booting time of servers can take between few minutes to tens of minutes. Most of the booting time is spent in checking status of the hardware, like running post. Skipping this post step can reduce the booting time significantly. Using a custom bootloader and shortening the boot time, we can provision nodes faster than traditional provisioning methods. For tenants of Recursive HaaS with some degree of trust among themselves, this service can allow nodes to be moved in seconds compared to minutes taken by base HaaS. Shorter boot times, along with faster deployment of OS across servers, opens up possibilities for a class of applications that require massive compute power for a brief period of time.
For Recursive HaaS, the main goal was to develop the recursive client that handles commands for bare hardware interaction and manages recursive resources. This will allow third parties to host HaaS and have the same functionality as base HaaS, and also to create an environment that's isolated enough to develop Recursive HaaS features. We developed these initial goals in a formal project proposal before beginning development and worked towards them using a Scrum developmental workflow. For some of the calls used in the HaaS project, many can be used without modification either recursively or otherwise. For some of the API requests, however, such as head node, networking, and console access, we modified to pass calls recursively up to the HaaS base head node to handle. Additionally, we were also able to contribute API functionality to the HaaS project itself.
In the top left of the screen, we start the base HaaS server. On the top right, we start the Recursive HaaS server. The command list free nodes will show us nodes not yet assigned to projects at each HaaS instance. The command list project nodes shows nodes assigned to a project. In this case, the bproj nodes have been provisioned by the recursive client. In Recursive HaaS, we delete node 4 by first deleting the NIC assigned to it. We can then verify that the node has not only been returned to the free pool with respect to the recursive client, but it's also been detached from the project in base HaaS. Recall the top left terminal is the base HaaS server, the top right is the recursive HaaS server. When HaaS calls are made, you'll notice activity at the responsible server window. We've just created a project in Recursive HaaS and we're connecting nodes 0, 1, and 2 to it. Note that these operations only occur at the recursive client. Base HaaS is uninvolved. Now we create a head node at the recursive client. This does have implications for base HaaS. When we create a head node in Recursive HaaS, the call is passed down to base HaaS. The head node is created in base HaaS. It takes the name given to it in Recursive HaaS, but with the recursive project name, rproj, appended to it. The command show head node demonstrates two-way communication where the recursive client queries base HaaS to get the VNC port for the head node. Here, note the evidence of the naming convention. We'll further demonstrate two-way communication by showing how an error can occur at base HaaS but be passed up to Recursive HaaS. In Recursive HaaS, we can't create a head node of the same name since it already exists. We delete it, which also deletes the head node at base HaaS. Next, we recreate the head node, but only in base HaaS. Recursive HaaS has no knowledge of it. Now, if we try to create a head node of the same name in Recursive HaaS, base HaaS throws an error, passing the error back up to Recursive HaaS, preventing the operation from taking place.
To see an example of how we altered the base HaaS code, let's look at the head node delete call. The original base HaaS code is on the left, while Recursive HaaS is on the right. Notice that on the right, a check is performed to see if the HaaS instance is recursive. This allows the same code to be used at every layer of Recursive HaaS, including the base layer installed on bare hardware. However, Recursive HaaS can also be run on top of the existing non-recursive version of HaaS, and in fact that is what we have done for the demos in this video. If the instance is found to be recursive, the call is forwarded to base HaaS. An additional function, error checker, interprets the reply and raises any necessary errors. If there are no errors, the database is updated, reflecting the call's successful completion. As an example of how one might automate some administration of Recursive HaaS, we've written a simple script that keeps the number of nodes in the Recursive HaaS free pool within a specified range. We can see that currently, the base HaaS has 7 free nodes, while 3 nodes are assigned to the Recursive HaaS project bproj. In Recursive HaaS, the free pool is empty. All 3 nodes have already been assigned to the project rproj. We run our script, which has been pre-configured to keep the free pool at 3 to 4 nodes. The script sees that the Recursive HaaS free pool is below the target range and reassigns 3 free nodes from base HaaS. We can use list free nodes to see that these nodes have now been reassigned. Suppose we wish to reduce the target number of nodes. We do this by editing the parameters in the script as shown. Let's reduce the free pool to a maximum of 2 nodes and a minimum of 1. This time, the script sees that there are too many nodes in the free pool. It reassigns one of these nodes back to base HaaS. We run the script again one more time, and it confirms that we are in the target range.
Now we will demonstrate fast provisioning. Here is the setup for our demo. For the purpose of the demo, we assume that the compute node is already booted into Fast Provisioning Bootloader or FPBL. As a custom OS, we have compiled a Debian operating system and it is pre-installed with all necessary functionality. One necessary condition for all the tenants of the Recursive HaaS will be to include kexec tools in their custom OS. The workflow is as shown in the diagram. The tenant will copy the customized OS from their head node to the compute nodes using SAP and then kexec into it. Run their application. When they're done, they can exit by reloading FPBL using kexec script already provided. Let's start with booting the compute node that is pre-installed with Fast Provisioning Bootloader. While it boots, let's look at the contents of the customized OS, which is already here on the head node of the tenant. This custom OS is pre-installed with application that does a simple matrix multiplication. We will copy the contents of the customized OS to the loading bay folder of the compute node using SCP. Let's SSH into it. Just to confirm that we are indeed logged into the compute node using FPBL, the configured address is this: 192.168.56.13 and some other information like the kernel version and the OS type. As you can see, the destination where the custom OS will be copied is currently empty. Let's start copying from the tenant OS to the compute node. Okay, it is a requirement for the customer to provide a script for switching into their OS from FPBL. This one is a simple script that uses kexec to switch between the two OSs. Let's ping to the custom OS just to see how fast it switches from FPBL. We have hard-coded the IP address of 192.168.56.20 for the custom OS. We will have to be root to be able to execute the switching script. Switching to the custom OS. As you can see in the bottom right window, which is the VirtualBox console window, it shows the process of switching from FPBL to the custom OS. Yes, we have to be root. Once the switch is successful, we will start seeing ping response in the bottom left window. There you go. Now we can SSH into the custom OS and do something useful. So let's do that. But first thing first, let's confirm that we indeed booted into the custom OS. This is a different kernel and different OS. Also, the IP address is different. as expected. We can also confirm this from the output of the console at bottom right, that it was the same node that switched from FPBL to customized OS. This particular OS is customized to multiply matrices of arbitrary size, demonstrating the same here. Once the program successfully finishes its job, we can use the script provided by FPBL to switch back to it from the custom OS. So after we are done multiplying this, for convenience, I have created a shortcut to the script here. No, not here. Here. As you can see, it's a symlink. For safety purpose, only root can execute this script. If we try executing this script as a non-root user, it will complain like this. To demonstrate the speed and confirm that it indeed switches back to FPBL, we will ping to both of them in the top windows. Left window is pinging to the custom OS, right window is pinging to FPBL, to which it will start responding once the switch is successful. Console at the right window will confirm that it loaded the new kernel. In principle, this whole process can be optimized to suit different scenarios where a single physical machine can quickly context switch between multiple customized OS to perform distinct operations in quick succession. There you go. We have switched successfully. Let's log in back to FPBL. Beyond the obvious economical and utilization benefits, this opens up a big solution space for applications that may need massive compute power for short periods of time. Thank you.
Now let's talk a little bit about what we learned from the class. In the course of working on this project, I learned a lot about how nodes are managed in a data center. I had relatively little experience with Python coming in, so this was a great opportunity to get more proficient with the language. Finally, I had never worked on an established code base, so digging into and modifying an existing project written by other people was a new experience for me.
Like Laura, this was my first opportunity working on a living, breathing code base. I was able to learn how command line arguments, APIs, database schemas, and servers work together. While I came to the project with a chunk of Python experience, this was my first opportunity seeing Python outside an academic context. Decorator syntax was new to me, and learning it allowed me to become better versed in Python as a language. Finally, by working with the base HaaS API, I learned about the topology of a data center, getting practical experience with networks, head nodes, and the nodes they service.
I learned a lot about working on an open source environment as well as the Agile Scrum workflow. I had previous experience with Python, but decorators were new to me. I also learned about project management as well as the dynamics of working in a small developmental team. In the end, I gained valuable exposure to the architecture of a data center.
I have had few years of experience managing data centers, but my coding skills were limited to writing procedural code in C and Python. Over the course of this project, I learned a lot about object-oriented Python, especially how object relational mappers interact with the database. Interacting with RESTful API, learning agile methodology, and using tools like GitHub, Trello board were among the things that were completely new to me before this project. In the quest of implementing fast provisioning, I got exposed to the intricacies of operating systems and memory management. Working as a part of team, contributing to a real-world development project was also a new experience.